There's two more reactions involving water. We've introduced condensation already. I will remind you an example of a condensation reaction. In fact, I'll go straight to the new condensation reaction that we're responsible for. You need a catalyst. Most popular one there by far. And we're going to do an alcohol. And the result you get, copy everything. The result you get is this. And you also get water. It's going to be a black H on your water and a blue OH. And this guy, there's more to him than meets the eye. This is called condensation, right? And that's an intermediate. Chromate ester intermediate. Comes from which acid? Chromate esters come from carboxylate esters come from carboxylic acids. Chromate esters come from chromic acid. Okay. And when you make a chromate ester, they are not stable. They undergo oxidation. And you get three products from two. Ketone, in this case. Hydronium. And reduced chromium. Cr plus 5 when you used to have Cr plus 6. 6 bonds to oxygen versus 5. Big picture. Then we can fill out the blank upstairs. Because all you have to do to fill out the blank here's the condensation reaction. I know you're furiously copying. There's the condensation reaction. The opposite would be water reacting with your chromate ester in the presence of the same catalyst, sulfuric acid, to make chromic acid and this secondary alcohol. So water was used, alcohol. Water was used to break down a bigger molecule into two smaller ones. The name for that reaction is, you already told me before the video, hydrolysis. So we could do a quick hydrolysis mechanism later. Actually, you're not responsible for hydrolysis just yet. We will briefly bring it up in a quick addendum to the end of this video. That will be the only example you'll see, and you're not responsible for a hydrolysis mechanism yet. Not till next course, okay? Chem 242. So this is a classic condensation reaction. Making esters, learn it now. You'll get points on it for 5 more exams. I am not lying. There's a condensation mechanism on every test in Chem 242. And they're very similar to this condensation mechanism. Very few changes at all. So if you get real solid on condensation in this course, you're doing yourself a big favor for the next one. Because condensation reactions are how things are made. In biochemistry, big molecules are made by condensation reactions over and over and over to make bigger and bigger and bigger molecules. First step is to protonate something. And my lab students might remember, because they did a condensation reaction when they did a Fischer esterification. And they don't remember now because it was a while ago. But they remembered they had to protonate the double bond to oxygen to activate. In that case, it was a carbon. In this case, it'll be a chromium. So one of the double bonds to oxygen, you pick. They're equivalent. It doesn't matter top or bottom, but don't pick left or right. They don't have double bonds. They can't resonate the product. So it's got to be one of the double bonds to O. You protonate and make an oxonium ion. The reason you did this was to make the chromium more reactive to alcohol acting like a nucleophile. And now we know about alcohols being poor nucleophiles. Chapter 9, we learned that. The reason you had to do this step was because the alcohol is a poor nucleophile and it won't do the next step until you've protonated that O. Now, that chromium is feeling a lot like oxygen's yanking on those electrons, saying, I got a plus, and I need my electrons back. And chromium's starting to feel even more positive because of that. Lone pair on the poor nucleophile attacks chromium. Lone pair on the poor nucleophile attacks chromium. So this is the synthesis part of condensation. What do I mean by that? The synthesis part. You're making the bigger molecule. That's what synthesis is. We haven't lost the water, which is later. Remember, I objected to the biologists calling it dehydration synthesis because it was backwards. As you can see, the synthesis happened first. That's an oxonium. We've generated oxoniums at least 20 times in this class. That is an understatement. This next step we did with like 18 out of the 20. Make oxonium that has a pKa of -2. Neutralize the oxonium. Then I'm going to draw the result very carefully. Yes, it looks like I forgot an atom. I did that on purpose. I'm recolor coding my water above, and you probably can figure out why now. I've got to make this molecule lose the green stuff. What's another name for the green stuff? Water. What's a reaction that takes a molecule and makes it lose water? All right. Takes a molecule and makes it lose water. What's it called? Dehydration. Now you're going to do dehydration. This is not a dehydration synthesis here, is it? We did not make a bigger molecule. Please do not think the dehydration has anything to do with synthesis. They can be combined, in which case we've done the synthesis already. It is now time for the dehydration. You need an acid-base pair. You need to just remind yourself, if I'm not seeing by the end of this semester that dehydration step has almost exactly the same arrows as tautomerization, then I'm not quite there yet. I need to think about it some more. Dehydration mechanism of this species here, tautomerization mechanism, virtually the same. You need an acid-base pair for either one. And please don't start bringing hydroxide into this reaction. You will not like the result. You're not using a combination of hydroxide and water as your acid-base pair here. You're using a stronger acid called sulfuric acid and its conjugate base, the thing you've been using already. Sulfuric acid was a catalyst here. You used it. You made it. You need to use it again. Okay? Draw sulfuric acid another time. HO3, SO minus, close to the alcohol of H. The other sulfuric acid close to the alcohol, which needs to leave, which is the theme of today's lecture. How do you make an alcohol leave in today's lecture all day? Make it a good leaving group by doing what to it? Adding a proton. That will be part of your mechanism. Tautomerization says grab an H using the base. Make a pi from the bond that used to be to H and the next atom. Protonate the O to make it a better leaving group, and then do what? I mean, you just said it. Why did you protonate it? So that you could make it do what? Leave. Okay, here it's leaving, but only because you protonated it. It would not have left unless you protonated it. If you had it leave as hydroxide, you will not like the result. You're not allowed to have hydroxide in any mechanism where there's a strong acid on the page. This is not the first time I've said this. If you look back at previous semesters, it's probably the 20th time I've said it. 20 is my number today, I don't know why. Okay, so there's a lot going on here. Very important. But anytime you need to make an ester with an acid catalyst, this is the mechanism. Okay? And that last step that's called dehydration looks just like tautomerization mechanism. Do them beside each other to verify. Okay? And you've got that. And then the oxidation is cool. I have one question for you. Here's water. Here's hydronium. They're a conjugate pair. Where'd water get the third H from? Which of these 5 carbon atoms loses an H? You just need to look at stick figures. You don't need to know any chemistry other than stick figures. The one with the O has an H now, does not have an H here. Please draw that H on the carbon. What takes that H? Please look at the products. Where did the third H go? Well, I gave the answer. It's water that got a third H. This mechanism also looks like tautomerization, which looks like dehydration. Grabbed H with base. Grabbed H with base. What's next? Same thing as you did next. Sigma becomes pi. Sigma becomes pi. If you look at the part to the right of the oxygen, it is HCr3O. HCrO3, sorry, my bad. This thing, HCrO3. Have it leave. We don't usually put lone pairs on metals, but that chromium being +6 is why this happens. It doesn't like being +6. It needs to get an extra electron. So the driving force is to get chromium reduced. And carbon got oxidized. Carbon got oxidized. And that's the importance of this reaction. We call it oxidation of a secondary alcohol, and it produces a ketone. It's a nice way to go. So we're going to stop.